geometric properties of Gaussian processes, especially to Brownian motion. Last time we discussed interesting things related to probability that Brownian motion will hit some set. So we discussed the following probability that there exists some peak which is greater than 0 that are Brownian motion v t will belong. We take some wall, for example, z epsilon. It is open wall, its center is the point z and radius x. And we start to discuss this probability. What we already did, the proposition was for let us consider this probability as a function of initial starting point. So we introduce the following function. And what we know about this function? Of course, it is trivial that it is measured with respect to x, and f is acting from RB to 0, 1. Well, this is probability. So it is bounded measure function. But last time we discussed interesting thing. So we discussed that if we have a ball with center point x 0 and we introduce the first time when we hit the boundary of the ball, the sphere, let's say it have radius r small. The tau will be infinite of such t that norm dt minus x 0 is equal to r small. So we introduced this stopping time, and we know already that probability x0 that tau is less than it is equal to 1. Also, we discussed the distribution of the point where we hit the boundary. This point evidently is b from tau, and we already said that distribution of b of tau is unique. So b of tau has uniform distribution. On the scale. This allows us to use strong Markov property of Brownian motion for this situation. So when we are looking for the probability to hit some set, even it does not matter that this is the ball, we can put it somewhere here. Our set that it is evident that before to hit this set, we have to enter the boundary of this ball. because we start from. So after this, we want to hit. It means that our function f, which we introduced, must satisfy some interesting relation. It satisfies some interesting relation, and we discussed this relation last time. It occurs that f of x0 is the integral with respect to s x0 r. So this is a sphere with the center at x0 and the radius r. Here we have the same function f, for example y, and here we have sigma r dy, where this is a uniform distribution of surface measure on our sphere, normalized to 1. Yeah. So we have such a good property, and let me know that this is for any r which is radius nothing. Of course, here I put for any, but the situation is formed. Here is our set which we want to hit, and here is our ball. We can take this one, but of course we cannot take this string when our ball will include our set. So, but it does not matter because I need this property only for all r which are sufficiently small. Because together with the measurability and boundaries of our function f, such property implies with necessity that the function f is continuous, is differential, and is harmonic. So this property, together with measurability and boundaries of function f, implies that Laplace operator of f is equal to 0. So f is harmonic function. F is harmonic function on our space. And this is a very powerful remark. We will have a lot of good consequences from this remark. Let us try to make such consequences. I will consider the following situation. I will consider d dimension, which is greater or equal to 2, and discuss the following question. We will have two spheres with the same centers. One is with the radius r small, here is the center x0, and another one is with the radius r big. So we have a multi-dimensional ring between these two spheres. Then let us start our Brownian motion from some point x inside z. So this x is placed between two these spheres. The question is the following. What is the probability to hit, for example, R small first place? I wrote R small to hit R small. It means that we will hit the smallest sphere with the radius R small. Just for short notation. So I will ask for such probability. Why we can do this? Because we already discussed that Brownian motion in arbitrary Euclidean space with probability 1 will leave any bond. So with probability 1, our Brownian motion will go outside of the ring, but it can go through this boundary or through this boundary. The question is, what is the probability that we firstly go through this boundary? Yeah. So we see such problem, and we will solve this problem explicitly very easy. Why? Because we can do the same as before. So we can see a small ball around of X and make the same conclusion. So I definitely know that if I will introduce such a function X, then it will be harmonic, and now I know something else. I know that here it is equal to 1. So f of x is equal to 1, then norm of x minus x0 is equal to r small. And here, on this boundary, part of boundary of our ring, f is equal to 0, because we already are on the boundary, and we go out through this one. So f of x is equal to 0 when norm of x minus x0 is equal to r. So we have such a problem related to the Laplace equation with these boundary conditions, and we can easily solve it. From the general theory, we know that the solution exists and is unique, and our idea is just to propose some solution. We can construct it using the harmonic function, which is symmetric under rotation with respect to x. So let me propose to you harmonic function, which is symmetric under rotation with respect to x. The kind of this harmonic function will be different depending on the dimension. So I will separately consider case when d is equal to 2 and case when d is greater or equal to 3. Let us consider firstly two-dimensional Euclidean space. So, in this case, let me propose to you the harmonic function. This will be a logarithm of the norm of x minus x. Please check that this is a harmonic function and that this function is invariant under rotation with respect to x. This is trivial because it depends only on the distance between x and x. When we have such harmonic function, then it is more or less easy to solve this problem. I can propose the following solution. F of x will be equal to the fraction. And here we have a logarithm of r minus a logarithm of r small. And here we have a logarithm of r minus a logarithm of a norm of x minus x. And you can see that, first of all, this function is harmonic because this is just a linear function from this one, and it is evidently harmonic. Secondly, when x minus x0 has a norm equal to r small, we have here 1. And when x minus x0 has a norm equal to r big, capital, we have 0 here, so we have 0. So we solved our problem, and let us do the same for another dimensions. After this, we will analyze the solution which we get. Okay, so this was the solution for dimension 2. Here is it. Now let's go to dimension which is greater or equal than 3. Consider dimension which is greater. In this case, we know already that the harmonic function which is symmetric under rotation with respect to x0 have a following. It will be like 1 over norm x minus x0 in the power p minus. Here is the potential. By the way, in D equals 3, this is Newton potential. So further construction is exactly the same as before. What we did, what we will do, we have a f of x, our probability. Again is a fraction. Here we have r small in 1 over r small in d minus 2 minus 1 r big r capital in d minus 2. Here we have 1 over norm of x minus x0 in d minus 2 and minus 1 capital in d minus. This is our solution in a case when dimension is is greater or equal to 3. let's verify. It is harmonic because it is a linear function from the harmonic function. And when this norm is equal to R small, we have 1. And when this norm is equal to R capital, we have 0. So we find our probability, and now we can analyze this solution. Let us do it. Let us begin from t equal to 2. Consider again the picture. Here is our small ball with a center of x0 and a radius r. And here is the big one. With the center at x0 and a radius r capital. I will start from the following procedure. Let us put this R capital go to the infinity. So suppose that R capital is going to plus. What we will have for this probability? What we will have for this probability? To understand this, let us consider the trajectory of our Brownian motion, which start from the point x. It is just a continuous line, continuous curve. Yeah? We know that it is unbounded. When we let R big, R capital, go to infinity, we just think about the probability at some time to hit this wall. Yes, because if we hit this ball at some time, we will have the continuous line, which have here the beginning and here the end. So it is bounded. So we definitely will have some R, which capital, such that this big ball contain all this trajectory. And for this trajectory, we will have this event. We firstly hit the small R. So one can understand that when R capital goes to infinity, then f x goes to probability that there exists some t which is greater than 0, then our bt minus x0 is equal to r small. So this is exactly the when R capital goes to plus. You see, this is exactly the probability which we discussed last lecture. And now we have the efficient way to calculate it, because we know the expression for fx. Let me put it here. Fx, let me recall you, this is two-dimensional. This is equal to ratio of logarithm of r minus logarithm of r small, and here is logarithm of r minus logarithm of log of x minus x 0. Now r small, x and x0 are fixed. Only we let this capital R go to plus infinity. Then what happened? When this R goes to plus infinity, it is evident that this ratio goes to 1. Yes, it goes to 1. From this point of view, one can conclude that this probability is equal to 1. And we have the following corollary, which is useful to write. Probability that our Brownian motion hit arbitrary ball is equal to 1. This is very interesting consequence, because see what happens. If we want now to draw the picture of the Brownian trajectory, we must note that if we start from beginning of the coordinates and put here any point x0, for example, then what will happen? Brownian motion will go near the x0. For example, we put here very small radius r with probability 1. We take another point, another small point. It will hit this ball too. We take here this ball, it will hit this ball too, and so on. So we can say with probability 1, trajectory of Brownian motion in two-dimensional case is dense on our plane. You see? This interesting consequence. Our Brownian particle travels in such a way that we almost visit any point of the plane. We cannot say that it visits point definitely. We will look, but it hits any ball, any small ball near this point. So if we are tourists and we are traveling according to Brownian motion, we can say that we definitely will see any historical places in the world with a rather small distance. For example, we can go to Coliseum with distance 1 kilometer, 1 meter, 1 centimeter, 1 millimeter, and we will do. Yeah? So we see that we have a dense trajectory. By the way, this is another proof of our already proved property of planar Brownian motion, that with positive probability it has intersection. Of course, such a curve which is dense on the plane must have intersections. Now let's see what about the visit of the point x0 itself, because there are some tourists which wants not only to make a photo but go inside. Yeah. So let us ask for such what is the probability of that there exists such T that BT will equal to X0. Will equal to X. To understand what happened, let us came back to our initial probability. Firstly, at the small sphere in the planar case, and now I will let this small r goes to 0 plus. So let us consider r going to 0 plus. What it will be? Again, to understand which probability we will have in the limit, let us consider such kind of the picture. Here is big ball, the radius r capital. Here is small one of the radius r small. Here is our point x, starting point. Suppose that we want to understand the probability of these events when we visit exactly our point x. Then our trajectory must have the following kind. Yeah? And as we said, it is continuous. So we have continuous line again. It must be bound. So for some r, we have the following picture. And for this r, the following event happens. We will leave this ring through the small boundary for any small r. But let's see what happened when we have this small r going to 0 plus. It's also very easy to calculate because r big, r capital now is fixed, x and x0 also are fixed. So we see that this logarithm goes to minus infinity, but we have here minus, we have plus infinity, and all this ratio goes to 0. So for any r, the probability that we will hit this x0 with the trajectory inside the ball of radius r is equal to 0. Now, letting this capital R go to infinity, we have that this probability that we will hit some fixed point is equal to 0. This is bad news for our tourist who is traveling accordingly to Brownian path on the plane. So we now know definitely that he will pass near collision, but he never will go inside. Yes, he will go arbitrarily close, but he will never go exactly in this point. This is about the two-dimensional case. Now let's came to the dimension 3 or bigger and discuss the same questions. So now consider d, which is greater or equal to 3. Then, as we discussed, our probability to leave the ring through the small sphere have simple but different from this kind. We have the following ratio here we have 1 over r small d minus 2 minus 1 r capital d minus 2. Here we have 1 over norm of x minus x0 d minus 2 and minus 1 capital d minus 2. So now our probability has a following time. And let's do the same as in the planar case. So I take capital R and let it go to infinity. What will happen here? The situation is rather different. The situation is rather different from the previous one. You see, when capital R goes to infinity, we just have a limit which is not equal to 0, but it also is not equal to 1. So this fraction is going to the following direction. Let me rewrite it in a more convenient way. This is r in d minus 2, and here is norm of x minus x0 in d minus 2. So this is a probability. Ever hit the ball with center x0 and radius r. And you see, this probability is not equal to 1. It is strictly less than 1. Yeah. Okay. So we have such an expression, and we will see that when r goes to 0, it goes to 0. So the less we have, the less this radius is, the less the probability that we ever hit this ball. And also, which is very important, this probability also decreases when the distance between x and x0 increases. Yeah? We see this phenomenon. So we have such kind of relationship. We don't hit the fixed ball with probability 1, just with this probability. Let us write it again. The probability that there exists such recurrence BT, the BT minus x0 is the norm r small is equal to r d minus 2 and divided by x minus x0 d minus 2. This is the first one. Now let us again think about the limit when r small tends to 0. Let us consider this probability. And now I fix r capital. And consider the following limit that r small goes to 0 plus. Evidently, this ratio goes to 0. Yeah. So, as exactly as in other case, one can conclude that we will visit the fixed point with probabilities. Exactly as it was done in the Plummer case. Okay. Now, let us think about the behavior of the trajectory at infinity. So, I want, using this representation, using this fraction, I want to discuss the following. What happened with the norm of the Brownian motion when t tends to plus infinity? When t tends to plus infinity. So, what will be the behavior? We have enough tools to solve, to answer this question. Let's see. Let's again draw a picture of our two spheres. One is big, another one is small. Then, see what happens. If we suppose that this is a hint. I already give a suggestions about the behavior of PT. I am going to prove that norm of PT goes to infinity. That the norm of PT goes to infinity. So I am going to prove this relationship. How we can do this? Suppose that the opposite statement is true. It means that the lower limit of this norm PT is less than PT. Yeah? So this is a contradiction. Okay, let us think what conclusion one can have from this hypothesis. It means that one can have the following, maybe if this is equal to some R0, so one can introduce another one R prime, which is greater than this one, and then we will have that our Brownian motion behave like this. Here is our R prime, and then we just start, for example, from the center of this ball, then go somewhere, then visit this ball, then again go somewhere, again visit this ball, and so on. But what we know, we know that we definitely have, we already proved this with you, we definitely have unbounded trajectory of Brownian motion. So what is true, what we know, that this one, upper limit of when t is going to plus the norm bt is equal to plus E. Okay. So we definitely know that we will cross any sphere of arbitrary large radius. But after this, because of our hypothesis, we will go back to this ball. So let us take Rn. Let us take Rn, which is going to plus E. Then we will have the probability that we get such a trajectory is smaller than probability to start from this sphere and hit this ball. We have fixed radius, and this distance goes to infinity. You remember that probability starting from somewhere from x and hit the ball of radius r small with the center at xu is the following. Yeah? And now this distance goes to infinity. So this ratio goes to 0. And as we mentioned, such probability is definitely larger than probability that we have to this relation together. Yeah. Consequently, our assumption was wrong, and we have this relation which we discussed. So now we understand a very good corollary for housekeepers that dust which live in our room and moves accordingly to three-dimensional Brownian motion disappears without any our efforts. It just goes out. Unfortunately, another dust go inside our room, so it does not work for housekeepers, but for scientists it is true, and it is very interesting fact. The Brownian particle in dimension 3 or larger goes to infinity. Now, when we understand the more or less the behavior of the trajectories of Brownian motion, let's try to think how to characterize its geometry, not only in qualitative sense, like we said, for example, in planar case. It is dense everywhere, it visits any ball with probability 1, or it visits ball with a smaller than 1 probability in three-dimensional case, or it goes to infinity. These are very interesting properties, but these properties have no qualitative, have no expressions in formulas. So now let us try to find right measure of the chaotic behavior for Brownian curve. We'll start from two-dimensional case again, because it is very interesting from the geometrical point of view. I just recall you the theorem of Dvoretsky-Erdős-Kaputani, which we already mentioned last time, that planar Brownian trajectories, probability 1, have points of intersection of arbitrary multiplicity. So, for example, we can find the point at the plane where the trajectory of Brownian motion crosses this point, for example, 1 million times. Yeah, it is very surprising. But this again is just qualitative statement. There are such points, but the natural question arises: how many such points exist, or how many times our Brownian motion spent near this point? And now we are going to the notion of the local time, or local time of self-intersection for Brownian motion. So let me introduce to you the notion of the local time. I will consider different dimensions, and now start with the one-dimensional Brownian motion. So I suppose now the dimension of Brownian motion is equal to 1. We know already that the even one-dimensional Brownian motion demonstrates very complicated behavior. Why? What we know? We know that it has no derivative, for example, and it has only one point of global maxima on the fixed interval, for example, and we know that it has a lot of roots near zero. So on any interval which contains zero, we have a lot of roots of the Brownian motion. If we have a smaller interval, still we have roots here and so on. So on any interval which contains zero, we have infinitely many roots of the Brownian motion. This behavior is drastically different from which we have in real analysis for smooth functions. Yeah? Usually we have a picture like this. We have 2 or 3 roots of the solver. Yeah? We have a habit to analyze the function using its derivative, consider its roots, consider the roots of derivative, second derivative, and so on. But all this analysis cannot be applied to this case. Yeah. So, what we can do? You remember we already count number of crossing for Gaussian process. Yes, we even produced a so-called Rice formula for this number, and it was a good tool to calculate all the characteristics for the level sets of one-dimensional Gaussian process. But in this case, we will go slightly faster. Let me introduce to you the definition, then we will see what happens. So, I will consider for epsilon, which is greater than 0, and some fixed point x, which belongs to R, such an expression, a small indexed by epsilon, x and depending on x and t, which is equal to the 1 over 2 epsilon. Here is integral from 0 to t. Here is indicator of the interval x minus epsilon, x plus epsilon, from our Brownian motion as ds. So this is not very complicated expression, but it seems rather unusual from the first look. Because of instead to investigate continuous function, we remember that this trajectory is continuous. Locally, just trying to find some substitution of its derivative and so on, we consider integral characteristic of this function. But it has a very clear and simple geometrical meaning. Namely, what happens if we consider a picture with graph of this Brownian trajectory on the interval 0 t. It starts from 0 and has the behavior like this one. Then one can take a level x, and have a small corridor near x of the size epsilon. We just have this one. Then this integral exactly express how many times our process is spent inside of this corridor. So we see that, for example, this interval must be calculated because we are inside of the corridor. Then this interval must be calculated because this part of trajectory is inside of the corridor. Then this interval must be calculated because of this part of trajectory is inside of the corridor. And also this interval must be calculated because of this part of trajectory is inside of the corridor. And this integral is exactly the sum of the length of these intervals. Then what we do? We divide this time which we spend inside of the corridor on the size. And what is it? It occurs that there exists a limit. There exists a limit when this goes to, when epsilon goes to 0 plus. There exists a limit, and we will follow local time Brownian motion at the point x on the interval 0 t. So our future considerations on the next lecture will be devoted to the proof that this limit exists, that similar limits exist for the double or multiple self-intersections, and to relationship between these quantities. I emphasize these are quantities. We can calculate it with these quantities and the geometric properties of Brownian trajectories. This will be the subject of our next lecture. Thank you for watching.
Oh, Professor, thank you very much. So maybe it's the last class for this series lectures.
We have another one, yes?
Maybe we the class 8 maybe it's the last time, right?
Oh, you see, because I just suppose that we will have another one just to speak about this local times. Can we have it or not? Is it possible? What do you think?
Maybe I talk about to the students. As you know, next week we'll begin this.
Already have some studies. I see.
Yeah.
Okay, maybe next time. Yeah.
Yeah. Yeah. Thank you. So, Professor, could you give us some suggestion for our students who have interest in this topic? Maybe they are...
Yes, I have at least two suggestions. The first one is the following. Today in the evening, we will have the seminar, Malявin calculus and its applications, and you have the reference on this seminar, where Professor Xiachen will discuss the subjects related to this local times of self-intersections in the hyperbolic Anderson model. So it is a related subject and it will be definitely interesting to see. Another one is the following. Now with PhD student Kim Song Wong are trying to prepare the conspect of these lectures. Now I hope that we will do this, and then we will distribute it around the students. Okay.
Oh, thank you. So, also, if some students, if they have interest or question, can they email to you, write email? Or...
Exactly. They can contact me, and we will discuss something. And they can contact Katerina Glinina. She will be in campus. So we even can organize some seminar for further study of this subject, if it will be.
Professor.
Yeah.
Can we join your seminar tonight?
Yes, surely. Professor Han has the Zoom reference, and you can ask him, or you can ask Katerina Glinina, or you can email me, and I will send you a reference. Okay.
Okay. Thank you.
Oh,
you're welcome.
Janan. And you? You want take part in the seminar, Professor?
Yes.
Okay, maybe yeah, I'll tell you the information. Yeah.
Okay.
Very good. I like to discuss it with Professor Xie Chen, and he said that he will carefully prepare his talk, so it will be definitely interesting.
Okay. Thank you.
So
okay, thank you for your attention. It was my pleasure to give this series of lectures, and I hope we will discuss the subject in future seminars, lectures, and so on.
Yeah. So thank you, Professor, very much.